Hello viewers, welcome to this second session in digital electronics and microprocessors part of logic gates second part. In this session we shall discuss certain topics that are extension of our previous session. In the previous session we have discussed about what a logic gate is and how the different gates are classified. Then we discussed about the basic logic gates, NOT gate, AND gate and OR gate. In this session we shall discuss about two more important logic gates that are called universal gates. They are the NAND gate and the NOR gate. Besides these gates, we shall also discuss an important theorem called as the Morgans Theorem, which will be very useful for you in designing higher levels of blocks using these gates. To realize any other gate, these gates will be useful for you. Besides, we shall also see the logical internal diagrams of various ICs that are manufactured to realize these gates. We shall also see certain practicals as to how to implement these gates on the logic trainer that you have in your laboratory. So, we shall begin with the two universal gates, the NAND gate and the NOR gate. The NAND gate is an extension of the AND gate. Here you can see the AND gate. When any inverter is placed at the output of the AND gate, you can get a NAND gate. Here you can see this is the AND gate whose output is A dot B. When this is given as the input for the inverter, you get the complement of A dot B. We call this as A dot B bar. By putting these two together, we can realize another gate called the NAND gate. So, this is the NAND gate. The symbol for NAND gate is AND gate followed by a bubble. So, given the inputs A and B, you get the output as A and B complement. So, here we define the NAND gate operation as the NAND gate is the inversion of AND gate, or the NOT of AND. NOT of AND is NAND gate. So, this is one of the two important gates of NAND gate and NOR gate. The symbol of NAND gate is an AND gate followed by a bubble. The truth table for NAND gate is an inverted version of the truth table of AND gate. As you may remember, the output of AND gate will be high only if both inputs are high. So, by that logic, the output of NAND gate should be low when all inputs are high. So, for this two input NAND gate, you can see the output A and B complement, as the output will be low if all inputs are high. So, here for the two input NAND gate, if the inputs A and B are 1, the output is 0. In all the remaining circumstances, when both are zeros or one of the inputs is 0, the output will be high. So, the realization of NAND gate and the logic expression the truth table are seen. So, here we say the output of NAND gate is low, output is low only if all inputs are high. So, this is low only if inputs are high. This is the NAND gate. We shall see the second important gate called the NOR gate. Here is the symbol for NOR gate. This is the NOR gate. The NOR gate is an inverter at the output of OR gate. So, not of OR is NOR gate. So, for a 2 input NOR gate, the output expression should be inversion of OR, that is, given the inputs A and B, here we get the final output at the end of the inverter as A ORed with B whole complement. So, this is the symbol for NOR gate. Given the inputs A and B, the output is A OR B whole complement. So, NOR gate is equal to not of OR, not of OR is equal to NOR. The truth table for NOR gate is given here. This should be, the output should be a complement of the OR gate output. As you remember, the OR gate output will be low if and only if all inputs are low. In contrary, in a NOR gate, the output will be high if and only if all inputs are low. In all the remaining cases, even if one of the inputs is high, the output goes to low position. So, in one sentence, we can say the property of NOR gate as the output is high only if all inputs are low. Here, the output is high only if all inputs are low. In all the remaining cases, you can check out the output is low. This is the truth table of NOR gate. The NAND gate and NOR gate are called universal gates in the sense that they will be useful for you to realize any logic gate. Especially to realize the basic gates, you need the NAND gate and NOR gate, because the basic gates are not very frequently used. Hence, in laying the gates on the IC, we require lesser number of types. So, we select only NAND gate and NOR gate for fabrication on the IC and realize all the other basic gate functions also using these NAND and NOR gates. So, you can see the NAND and NOR gates are called universal gates because using them it is possible to realize the circuit of the nature of any logic gate. We will be using the Morgans theorem and also the basic postulates of the Boolean algebra to realize these basic gates using the NAND and NOR gates. So, we shall see how we will be able to produce the outputs of basic gates using NAND and NOR gates. See here how a NAND gate is realized using the NAND gate, the NOT gate is realized. We know that the output of an inverter or NOT gate should be complement of the input. To achieve this, we will be using the NAND gate. But as you know, the inverter has only one input, whereas NAND gate requires at least two. So, to produce a single input from the two inputs, we short one terminal to the second and apply a single input A, in this case a single input to the NAND gate. Here we use the basic postulates of the Boolean algebra. The basic postulates have defined the AND function using a single literal as the ANDing of a given signal with itself produces the same signal, that is A ANDed with A produces A only. So, here we take the single input and give it to the two inputs of the NAND gate. So, at the output, since this is a NAND gate, the output should be A dot, that is A ANDed with A bar whole bar. Using the postulates A ANDed with A produces A, the complement remains as it is. So, given the input A, we have realized the output as A bar, that is the NOT gate is realized using the NAND gates. So, this NAND gate behaves similar to the NOT gate. We shall see how OR gate is realized using the NAND gate. The expression for OR is A ORed with B. So, here we will be using these NAND gates, NAND gate 1 and NAND gate 2 as inverters. So, given these two inputs to this NAND gate, when we apply the input signal A through this first NAND gate used as inverter, we get the output as A bar. Similar is the case when we apply the input as B. This NAND gate acting as inverter produces the output B bar. When these two inputs A bar and B bar are applied to this NAND gate, it produces an output A bar ANDed with B bar whole bar. Here, in order to realize these, we require to substitute or to get this expression of OR gate. From this we require the knowledge of De Morgan's theorems. So, shortly we shall see what De Morgan's theorems will state. Overall, this A bar ANDed with B bar whole complement gives you A ORed with B. See how we realize the AND gate using the NAND gate. The two inputs A and B are applied to this NAND gate, producing an output A ANDed with B whole complement. When this is further given complementing using the inverter, the double complement will be cancelled and we get the output as AB. Here the second NAND gate is used as an inverter. So, a NAND gate followed by inverter gives you AND gate. This is how we realize the three basic gates using the NAND gate. We shall see them together. When two inputs are shorted for the NAND gate, it produces an output equal to the output as produced by the inverter. If the two NAND gates are used with the first one as it is, but the second as an inverter, it produces an output equivalent to AND gate. If the two inverters are used at the input of the NAND gate, it produces an OR gate functionality. Now, we shall see how NOR gate will be useful for us to realize the functionalities of the basic gates. The use of NOR gate as inverter is on similar lines as that of use of NAND gate. So, here we short the two terminals and produce a single input A. Hence, the output should be A ORed with A whole bar. Our basic postulates of Boolean algebra say that the same literal when ORed will produce itself, that is A ORed with A will produce A. Thus, the final output is A bar, which is desired for an inverter. Hence, given the input A, we are getting the output A bar. Hence, here we are using this NOR gate as an inverter. Now, we shall see the other gate. The OR gate is realized using the NOR gate. Use the first NOR gate in its natural functionality, that is, given the inputs A and B, the output produced at the output of this NOR gate will be A ORed with B complement. When you use an inverter at the output of this first NOR gate, we get the output as A ORed with B. Hence, a NOR gate followed by inverter produces a functionality of OR gate. Now, we shall see how to get the AND gate realization using the NOR gate. For this, we use two inverters at the inputs of the NOR gate. So, given the input A, you use the NOR gate as an inverter to produce an output A bar. Similar is the case, B is given to a NOR gate acting as inverter to produce an output of B bar. These two outputs of these inverters are fed as inputs to the NOR gate. So, given the inputs A bar and B bar, the NOR gate produces an output of A bar ORed with B bar whole complement. There we get the output as AB. Hence, using the NOR gates, we have achieved the functionality of AND gate. This is how we realize the AND gate functionality using NOR gates. So, this is the AND gate realization. We shall see them together. When the NOR gate inputs are shorted and a single input is applied, the output will be the inverted fashion of the input. Hence, the NOR gate will act as an inverter. Similarly, when the NOR gates are used in tandem, the first one in its natural form, the second one as an inverter, we get the output as OR gate. When these NOR gates are used as inverters and feed the inverted values as inputs to the NOR gate, we realize AND gate functionality. This is the realization of the basic gates using the NAND and NOR gates. Now, we shall see an important theorem called as De Morgan's theorem, based on which we will be in a position to draw the equivalents and produce one expression that is equivalent to another expression, but in complemented and dual forms. So, here we see what the De Morgan's theorem states. The De Morgan's theorem states that the nature of output of a given expression will not change if we follow certain procedure listed as given in 3 steps. So, the statement is the nature of output remains unchanged if a given expression is changed. You alter the given expression based on the following lines, then the output will remain unchanged. The 3 steps you have to follow are: take the complement of each literal, then change all ANDs into ORs and vice versa, that is all ORs are to be changed into ANDs. Then take the complement of the entire expression. Following these 3 steps, it is possible to see that a given expression's output will not change even if the nature of the expression is changed. what the De Morgan's first theorem states is that the complement of AND is equal to the R of complements, that is A ANDed with B whole bar is equivalent to A bar plus B bar. This is the De Morgan's first theorem. So, A ANDed with B whole bar is nothing but a NAND gate. So, a NAND gate is equivalent to an OR gate whose inputs are inverted. So, A and B whole bar is equal to A bar plus B bar. This is achieved based on the De Morgan's theorem procedure laid out in the previous steps. So, here we have the first equation A ANDed with B whole bar. So, following the steps of the De Morgan's theorem laid out previously, we see the first step, take the complement of each literal. So, take the complement, A becomes A bar and B becomes B bar. So, they become A bar and B bar. Then here is ANDing. The ANDing, each ANDing change all ANDs into ORs and ORs into ANDs. So, change the AND into OR. So, we have A changed into A bar and B changed into B bar, and AND operation is changed into OR operation. So, A turned into A bar, B turned into B bar, ANDing turned into OR operation. Then take the complement of entire expression. So, we have A bar plus B bar whole bar, and this previous complementation continues. So, there we get double complement that gets cancelled. So, on the whole we get A ANDed with B whole bar equal to A bar ORed with B bar. This is the De Morgan's first theorem. Overall, we see that a NAND gate is equivalent to OR gate whose inputs are inverted. The complement of AND is equivalent to the OR of complements. So, A is turned into A bar, B is turned into B bar, and ORing of them is done. This is the De Morgan's first theorem. Here we see the second theorem of De Morgan. It states that the complement of R is equal to AND of complements. So, complement of R. So, R complement becomes NOR, A plus B, that is A ORed with B whole complement. It should be equivalent to AND of complements, AND of complements. A is turned into A bar, B is turned into B bar, and the output of this AND gate will be A bar ANDed with B bar. How this is made equal? This is also based on the three steps laid out previously. The first step should be to take the complement of each literal. So, turn A into A bar and B into B bar. It becomes A bar, B bar. The second step is change R into AND. So, this becomes AND, A bar ANDed with B bar. Take the complement of this entire expression. So, we get a double complement here which gets cancelled. Double complement because this is the third step is you should take a complement, whereas the second complement will be coming out from the A plus B whole bar. From here we get the second complement. So, that second double complement gets cancelled. Overall we get A or B whole bar equal to A bar ANDed with B bar. So, the complement of R, that is NOR, is equal to AND of complements. So, that is A bar ANDed with B bar. This is the De Morgan's second theorem. So, based on these two theorems, we have realized the previous logic gates. We shall summarize these two theorems together. Here a NAND gate is equal to A bar ORed with B bar, NOR gate is equivalent to A bar ANDed with B bar. These are the universal gates and De Morgan's theorem. Students, till now we have seen the basic gates and the universal gates, and also the realization of basic gates using the universal gates NAND gate and the NOR gate, and also how De Morgan's theorem will be useful for you to implement these conversions between various gates. When we move into the laboratory, we should be in a position to work with these gates. For this, we shall get familiarized with the various ICs used in the laboratory that contain these basic gates as well as the NAND and NOR gates. The first gate that we shall see is the 7400 TTL gate. This is a quad 2 input NAND gate. Quad refers to there are 4 such NAND gates in this IC, and each NAND gate is a 2 input NAND gate. So, overall this requires, each gate requires 3 pins, 3 4 folds becomes 12. With the ground and VCC terminals, we require a 14 pin IC for this. So, 7400 is one such IC fabricated to house 4 such 2 input NAND gates. See here, this pin 14 is used as VCC and pin number 7 is used as ground. That is, you connect the positive terminal of the supply at the pin number 14 and the negative terminal at pin number 7. Then you will be applying the inputs at gate at pin numbers 1 and 2, and you can observe the output at pin number 3. Now, we shall see physically how this IC looks like. Here this is the 7400 quad 2 input NAND gate. You can observe a notch at one side, the second side is flat, there is a cut in the first side. So, keeping the cut to the top and viewing from the left, the top pin is pin number 1. So, we come from pin number 1, 2, 3 as such up to pin number 7, which is the ground. Then move to the other side and count from bottom to the top as pin number 8, 9, 10 and come up to the last pin. This one is pin number 14, to which you connect the positive terminal of the supply that acts as VCC. This is the IC 7400 that houses 4 2 input NAND gates. Now, we shall see the other ICs. The 7402 is a quad 2 input NOR gate, that is, it contains 4 NOR gates with each NOR gate containing 3 pins. 2 are the input pins and the third pin is the output terminal. So, 4 NOR gates, hence the name quad 2 input NOR gate, because each NOR gate is of 2 inputs. See here, the 7402 is an IC that contains these 4 NOR gates. You can see the 7402. This is also on the same lines as that of 7400. You can see a notch over here. You can observe that there are 14 pins. So, starting from the left side of the notch, keeping the notch to the top and observing from the top left side, this is pin number 1. Then coming downwards, we move up to pin number 7, then pin number 8 and move to the top towards pin number 14. This will be VCC. This is a quad 2 input NOR gate. The 7404 is a hex buffer. Hex refers to there are 6 number of such gates inside this IC. Here as usual, this is a 14 pin IC with pin number 14 meant for VCC and pin number 7 meant for the ground. It contains 6 buffers, 6 inverters. Each inverter is having one input and one output as such. So, connect the positive terminal of the supply at pin number 14 and the negative terminal at pin number 7. We shall see how it looks like. This is the IC 7404 hex buffer. Inside this there are 6 number of inverters starting from the notch and left side 1 to 7 and 8 to 14. There it contains 6 number of inverters. The next IC we are going to discuss is about the AND gate 7408. It is a quad 2 input AND gate, meaning that there are 4 AND gates, each of 2 inputs inside this IC. So, starting from pin number 1, 1, 2 are meant for the inputs of the AND gate and 3 is for the output. As usual, the pin number 7 is for ground and 14 is for VCC. This is the IC 7408. It is a 14 pin IC containing 4 2 input AND gates. The next IC is the IC 7432. It is a quad 2 input OR gate, that is it contains 4 OR gates. Quad refers to 4, each of 2 inputs. So, 7432 is a quad 2 input OR gate. The pin numbers 1 and 2 are meant for the inputs and pin number 3 is for the output. You can see 1A, 1B, 1Y. These 3 are for the first gate. A and B refer to inputs and Y refers to the output. Similarly, the second, third and fourth OR gate input and output terminals. Ground and VCC are as usual. So, here 7432 is a quad 2 input OR gate. Here we see the 7432 quad 2 input OR gate. This is the IC 7432. So, dear students, till now we have seen the various universal gates, the realization of these gates and also how to implement these gates inside the ICs. Now, it is time for us to move into the laboratory. We shall see, we shall verify how these input output relations will be. So, we shall check with the first gate starting with the NAND gate. We introduced you to this logic trainer. These are the set of input switches. These are the slots from where you can take the input, that can be logic 0 or 1. This toggle switch is used to select between logic 0 and logic 1. From here we apply the inputs. This is IC 7400. This entire block contains IC 7400 that contains 4 2 input NAND gates. So, we shall select one NAND gate among them. So, here is that NAND gate, 1 and 2 are the input terminals and 3 is the output terminal. To these input terminals we apply the input from the input slots and the output is verified at the output slot. The LED glow indicates a logic 1 and if it is not glowing, that indicates logic 0. Now, we shall verify various logic conditions of this 7400. Here we have applied the 2 inputs. This glow indicates a 1 and when the glow is absent, it indicates logic 0. Now, under this situation, both the inputs are 0 0. You can observe that the LEDs are not glowing. Under the 0 0 condition, the output of this NAND gate is logic 1. Now, if one of the inputs is changed to 1, the output is still logic 1. If both are put to logic 1, the output is becoming 0. So, this is the verification of the NAND gate. So, you can observe that both inputs are high whereas the output is low. This confirms the truth table of NAND gate, that when all the inputs are high, the output should be low. If one of the inputs are low or all the inputs are low, the output will be high. This is the verification of the truth table of the NAND gate. Now, we shall see the verification of the truth table of the NOR gate. Here is the 7402 quad 2 input NOR gate. This is internally an IC 7402 is placed below this, that contains 4 such NOR gates, 2 input NOR gates. So, we shall insert these inputs at the NOR gate. Now, see here, the 2 inputs are connected to the input slots and the output from pin number 1 is taken and put in this slot. Now, we shall give the various combinations of the inputs. At the beginning, both the inputs are 0. Under this condition, the output is glowing, that is logic 1. When the inputs are 0 0, the output is logic 1, that is high. When one of the inputs is applied a high signal, you can see here input is 0 1. Under this condition, the output has become 0. Now, we shall see the other combination 1 0. Even under that circumstance, the output is logic 0. When both inputs are high, that is 1 1, the output is still 0. This confirms the truth table of the NOR gate, that is when both inputs are logically 0 condition, only then the output is at logic 1. So, this is the verification of the truth table of NOR gate. We have seen these verification using very much the same ICs about which we discussed. So, this is about the truth table and verification of the logic conditions of various gates. So, students, with this you have seen the logic gates part of the digital and digital electronics and microprocessors part of your subject EE 304. In these two sessions, we have seen what you mean by a logic gate, what are the various logic gates, what are the various basic gates, what are the universal gates, and how to realize the basic gates using the universal gates. The knowledge of these gates, logic gates, will be useful for you to construct or design higher levels of circuits, especially in your forthcoming chapters of combinational logic and flip-flops. We will be using the knowledge and during these two sessions, especially the NAND gate and NOR gate discussed in this session will be useful for you to implement flip-flops, which are memory units in your computers, and also the basic gates along with the universal gates NAND and NOR will be useful for you to construct higher levels of circuits, arithmetic circuits, say the adders, subtractors, multiplexers, demultiplexers, and all that will be useful for you to construct the control part of the computer. So, as though the logic gates appears to be a very easy topic, you should gain a confident knowledge in these, because it will be useful for you to get a knowledge of the design of other units, that is arithmetic and logic units in your next chapters. Hence, you should learn how to minimize a higher level of circuit into a smaller circuit, and also to design a higher level of circuit using the basic gates. So, I hope that you have gained enough knowledge about these logic gates and universal gates. So, thank you, goodbye.